In this video, we're going to talk about weak acids. I'm going to use the example of an organic acid. Organic acids contain carboxylate groups. And so the example we're going to use is formic acid, which is what fire ants sting you with that causes so much pain. The proton that's donated by the acid, so this is the donor, and so that makes this the acceptor, because remember, you must have a donor-acceptor pair on each side. For the reverse reaction, the H plus goes back to the original molecule, so this must be the donor for the reverse reaction, and this must be the acceptor for the reverse reaction. Okay, and so proton on gets donated away, proton off takes it back. The other thing that you can do when you diagram these is to link the molecule that both donated and accepted. And this is called a conjugate pair. Okay. And so you have to be a little careful that this being conjugate to that doesn't mean it's any less of a base when it accepts the proton. So this is an acid because it donates a proton. This is a base because it accepts a proton. And so that forms a conjugate pair. And then when you look at the conjugate pair, when you link them, there should be a word that says donor on one side and acceptor on the other side. The donor should have the proton on it compared to the acceptor with the proton off. And if you can do this, then you're fine. And of course, the other pair must also be a conjugate pair. This is also a conjugate pair. The acceptor, proton not on, the donor, proton on, and they differ in the formula by an H plus. These two differ in the formula by H plus. If these conditions are not satisfied, you have incorrectly written your acid-base reaction. Okay, so we can write down the equilibrium constant. And so just like the weak base had a special name for the equilibrium constant, Kb for base, then this is going to be called Ka, where this is the acid ionization constant. So it's products over the reactants, H3O plus, the conjugate base, HCOO minus, divided by the HCOOH. Okay, the liquid water is not included as part of the equilibrium constant. Turns out that the concentration of water is 55 molar, and it's pretty much unaffected by the small amounts of other stuff you put in it. And so it's kind of incorporated into the equilibrium constant. Okay, so we can look at this example. So formic acid at some temperature will probably be, if you throw in 1 molar, probably be about 1% ionized. Let's say 0.01 molar hydronium, 0.01 molar formate, and 0.99 molar formic acid. So this is going to be about 1 times 10 to the minus 2 for HCl plus and for that. And when we calculate that, that's going to be about 1 times 10 to the minus 4. And just as in weak bases, it turns out the magnitude of the equilibrium constant determines how strong the acid is. That is to say, how much H3O plus is floating around the solution. The stronger the acid, the more products you get. The more products you get, the larger the K. So a K for an acid that is a very large number compared to a K for an acid that's a very small number. The large Ka is a stronger acid than the acid with a very small Ka. Some of these Kas can be quite small, like 10 to the minus 10. I want to say one more about the chemical structure of carboxylic acids. The acidic proton is always written, well, always coming from an OH bond being broken. And then what's left behind is an O negative on that particular oxygen. This CH bond is not acidic. That's to say the hydrogen does not come off as H+, it doesn't come off at all, never breaks. And so if you were to replace this hydrogen by some other organic stuff, you get other organic acids. So for example, if instead of hydrogen you have a methyl group, CH3, you have acetic acid or vinegar. And most of the organic acids taste sour. So if you think of vinegar sour, Lactic acid is sour, and that's a major component of buttermilk, for example. And the other thing is to be aware that if you see a formula written COOH, it means a C double bond O and a COH. It's this proton that's acidic. Acidic proton, not coming off. So it's only this other proton that came off, not the one that bonded to carbon. So when you see an OO, don't think it's an OO bond. That's a peroxide. That is not at all a very stable molecule. They're very unstable and, as a matter of fact, quite explosive.